Now let's look how to optimize functions that have two input variables. So we'll focus on relative and local extrema in 3D. But first, in order to do that, let's review what it looks like in 2 dimensions. So recall we used first and second derivatives to find the local extrema of functions with one input variable. Now again, one input variable, that's 2-dimensional. You have an x and you have a y. We take the first derivative, set it equal to 0, or where it's undefined, and those are the values that gave us our critical points. The second derivative, set equal to 0 or undefined, gave us our inflection points, which determine concavity. When we're looking in a 3-dimensional picture, there's actually 3 possibilities when optimizing these functions with 2 input variables. In other words, it has 2 input variables and 1 output variable, thus 3-dimensional. The figure on the left shows a local minimum. It's like the bottom of a bowl. The second picture shows a local maximum, like the top of an umbrella. The third picture is called a saddle point. Think of a saddle on a horse. You have the maximum of left to right going, between the legs on the saddle, but you're also at a minimum point front to back. That's why it's called a saddle point. It is both a maximum in one direction and a minimum in another. So recall the graphs must be smooth and continuous to be differentiable. And we're not dealing with boundaries here, so no absolute extrema. Yay! Now, how do we find our relative extrema? We have to find our critical points. So they can occur only where the first partial derivative with respect to x equals 0, and where the first partial derivative of y also equals 0. So let's take a look at example A. We want to find the critical points for the function f of xy equals x squared plus y squared minus xy minus 3y plus 5. So our first partial ordered derivative with respect to x will give us a 2x in the first term minus a y in the third term, and the other terms don't have x, so they'll be 0. And then the first order partial derivative with respect to y, we would go to the second term and get a 2y. Our third term would give us minus x. Fourth term would give us a minus 3, and the other terms do not have a y, so they would be 0. So now we have to set both of these equations equal to 0. That's right, we're going to use a system of equations. So if we line these up, we'll call this equation A, 2x minus y equals 0. And equation B, we're going to put the x's in the front, so negative x plus a 2y, and we're going to add the 3 to the other side. So everything's lined up. We can use our elimination method, maybe multiply everybody in equation B by 2. So that would give us an A of 2x minus y equals 0, and a negative 2x plus 4y equals 6. Combining those terms now, we would get a 3y equals 6, which gives us a y equals 2. We have found the y. Now we have to find the x. We can plug that y back in. So let's say equation A. So 2x minus our y value of 2 equals 0. 2x equals 2, so x equals 1. So that means the point 1, 2 is a critical point.